Hey Danny, how's it going?
Oh, hey, Professor. Pretty good. How are you?
Good, good.
I remember when I had you for fluids. I think you had like an icon from your favorite game. It was just
hmm
I kind of forgot what it was. I'm just trying to look for new games to try out.
Oh yeah, it's Legend of Heroes Trails in the Sky.
Let me write that down real quick.
I'll send you in the chat.
Oh, okay. Is it like a JRPG or something?
Yeah, it's very JRPG. It's as JRPG as you can get, but but I love it. It's really slow. It's a really slow game, and so
Okay.
I've been unsuccessful in getting literally any of my friends to play it just because it's just way too slow for them.
What do you mean by
It's
slow? Like the
the
progression?
plot is really slow. So
Oh, oh,
so it's there's like three games in the series, although it's really there's really two games. And so there's Trails in the Sky, they call it first chapter, and Trails in the Sky second chapter.
oh, okay.
But the entire first game is basically just setup and prologue, and so
Oh, okay. So it's kind of like a
it's
three-part
really
series.
slow. Yeah, yeah. The second game is kind of when most of the stuff takes place, and the third game is like kind of epilogue, but also set up for kind of later in the series too. But Trails in the Sky kind of is a three game arc, and
Okay.
the entire first game is like like 60 70 hours. It's all just set up, and so
Yeah.
it's hard to sit through all of it.
Oh, so would you say on average every game's about 70 hours each?
Yeah, yeah.
Oh, okay. All
hmm
right, I'll dedicate my time to that.
Yeah, it's I mean it goes on sale on Steam quite a bit, and so I would wait for a sale because on a sale you can get it for like $10 or something like that.
Okay.
Yeah.
Yeah. Thanks for the heads up.
hmm All right, it's 1 o'clock, so let's go ahead and get started. Good afternoon, everyone. How's everyone doing today?
Doing good. How about you?
Good, doing good. Thanks for asking. I'm excited for the weekend. So Thursday is actually the end of the week for me because I don't teach on Fridays, and so Fridays are kind of when that's when I kind of catch up on a lot of other work. And so, but Thursdays are the last day that I actually have to wear a nice dress up. So for those of you who took any of my classes over the pandemic, you know that I'm always just teaching from my apartment in my pajamas. And so one downside to returning to the office is I actually have to wear something nice in case I bump into the dean in the hallway. And so Fridays are kind of my day just to be lazy and still do work, but do it in my pajamas instead of having to get dressed up. Yeah. Nice, turned 21. Congratulations, you can legally drink now. So yeah, so have a good weekend, but don't go too crazy. You want to be alive and well over the weekend. I remember when I turned 21, it was always, it's always a fun thing. It's always, a big turning of age. And I think it happens at kind of the perfect time in college too, when kind of you're, probably in your later years of college, and then, you're a little bit more aware of the world and aware of, what opportunities are around you. So, hope you have fun this weekend. Okay. So today, the plan is to finish up our lecture notes on present worth analysis. Okay, so we got about halfway through last time, and so today I plan to finish the rest of it. Okay, and so after today, you should be able to do the entire homework assignment. Okay, so I posted a new homework assignment earlier this week, and then the subject for that homework assignment is cash flow conversions to present worth. And so after today, you should be good to go with everything in the homework. Okay. All right, so there are any questions before we get started today? Okay, all right, so let's go ahead and get started. And actually, we left off at kind of an awkward place last time because we were stopping in the middle of an example. And so let me just kind of go back a couple pages just to kind of remind you what we were looking at, right? And so last time we introduced this idea of present worth analysis, where the whole idea with this technique is that you can take different economic alternatives and then compare them based on their costs and based on their benefits and see which one is the most economically efficient. Okay, because what we were saying is that over your career as an engineer, you're going to come across many situations where you're choosing between several different alternatives for your problem, right? Whether it be purchasing a new part, right? And so different vendors are going to offer very similar parts, or maybe it's selecting between two different business strategies. Okay, there's going to be a lot of opportunities for you to make an economic decision, right? And it may not be perfectly clear on which one is going to be the most efficient. Okay, and so we have this technique called present worth analysis in order to give us a systematic way to in order to see which economic options are the best. Okay, and the way we did that is we simply just took all the cash flows associated with the given option and just converted it to a present sum. Okay, because by doing that, by converting everything to basically a present day value, then you can do kind of an apples to apples comparisons between different options. Okay, and so we did an example of that last time. Okay. And then, before we left off on Tuesday, we were kind of in the middle of kind of an interesting situation. Okay, because the thing with present worth analysis is that you have to compare options that have the same product lives. Okay, and so you can't really compare one option that maybe has a product life of say maybe like 4 years. Okay, versus one that has one of 8 years. Okay, because that's going to mess up your calculations. Okay, and so if you ever come across those options, one thing that you can do is that you can, change it so that you basically set both of the product lives to be the same for both cases. Okay, and one way to do that is to select the least common multiple between their product lives. Right, and so in this example here, we have two different options. We have option A and option B. Okay. Option A has a product life of 8 years. Okay, and so you buy it, it's going to last you 8 years before it breaks down. But option B will only last you 4 years. Okay, and so in order to do kind of a fair comparison between these guys using present worth analysis, you have to extend the life of product B up until 8 years so that they kind of end at the exact same time. Okay, and the way we do that for cases like this where we have one product life that lasts less is to assume that we can buy a replacement, when that first one wears off, okay? And that's exactly what we're going to do here. And so for option B, we're going to buy a replacement after 4 years at the exact same cost that we did, the first one. And then that's going to take us up until the end of 8 years, okay? All right, and so here's the example that we were kind of, in the middle of right here, okay? So you're working for Southern California Edison, okay? So you're working for the power company. SC Edison basically saying that they need to purchase a new pump in order to expand its capabilities, okay? And there's 2 pumps that are available that serve your purpose well, okay? So vendor A is going to give you a pump that costs $7,000. The maintenance is $1,500 a year, and the salvage value is $1,200, okay? This pump is going to last you 12 years, okay? So it's a pretty long lasting pump. Versus vendor B is going to offer you a pump that's at a lower cost. And so vendor B is, the pump is only cost you $5,000. The maintenance is $1,000 per year. At the end of the period, you can salvage it for $1,000. But these pumps are a little bit lower quality. And so they, they can only last you for 6 years instead of 12, okay? And so, what I wanted you guys to determine is, I want you to use present worth analysis to basically compare these 2 pumps and see which one is the better option for you to do, okay? All right, and so where we left off on this example is that, we were drawing the cash flow diagrams for these, and you can see here for pump A, we have this cash flow diagram that lasts for 12 years, okay? And so it's a fairly straightforward cash flow diagram where we have just simply our initial cost at the beginning, okay? And so here we have our $7,000 cost, okay? And then every year after that, up until the end at year 12, we have a maintenance cost of $1,500 per year, okay? And at the very end, we can sell the pump for $1,200, okay? Right? And so we don't need to do anything for pump A because pump A is already lasting longer than pump B. And so we can just say that we're just going to buy one pump and then we're going to use that for our comparison between the 2. Okay. Okay. Any questions on anything so far? Okay. All right. So now let's look at the cash flow diagram for pump B. And so this is kind of what we left off on last time, right? And so pump B is only going to last us for 6 years, right? And so if we draw, the initial cash flow diagram for 6 years, we're going to have something that looks like this, right? And so we have our initial cost of $5,000, okay? And then every year after that, we have a maintenance cost of $1,000, okay? So that we're going to pay out every single year. And then at the end of that 6 years, we're going to get paid $1,000 for selling that pump, okay? But because since we're doing this analysis for 12 years, at the end of year 6, we need to purchase a new pump, okay? And so in orange right here, what I have is basically the cash flow for pump number 2, okay? And so pump number 2 is one we're going to buy in year 6. It's again going to cost us $5,000. Okay? The maintenance cost for this pump is going to be $1,000 per year up until year 12. And then we're going to salvage that pump for $1,000 at the very end, okay? All right. And so now what we have here is we have 2 situations where both of them last up to 12 years. And so now we can actually perform this comparison between them, okay? And so the next step in this problem is that we're going to convert, both of the costs for both these pumps into a present sum. And then from that present sum, we can say which one's going to be economically efficient, okay? Okay. All right, and so the results of this may surprise you because I think normally when you're given information like this, right? I think the tempting thing to do is to say that pump B is something that we're gonna have to buy twice, and so that one's probably going to be more expensive. So even though the maintenance is less, right? The fact that we have to buy it twice within the same period makes it seem like that's the least economically efficient option, okay? And if you're working for an engineering company, they might think the same thing too, because the whole kind of process of taking a pump offline and then getting a new one and then getting it on there, there's a lot of value in just buying the pump once and just having it run for 12 years. But from this analysis, you'll actually be able to see kind of the opposite. Okay. All right, question. So question in the chat is, if vendor A had an N of 15 years and vendor B had an N of 6 years, will we use a diagram for 30 years? Yes, yes. And so for those cases, for this case, the numbers work out really well, that the least common multiple is pretty small. But sometimes, you have to extend it a little bit more. And so, if your least common multiple, you have to go even more than that. That's one thing that you can do, but within reason as well. And so actually after this example, we'll go over a case where it's not feasible to use the least common multiple. Because actually, even in your case, Danny, 30 years is a really long time too. And it's really hard to predict stuff, that's going to go out for 30 years, because that's basically a person's whole career, right? And so to say that, you're going to be using this pump for 30 years, or these pumps for 30 years is, is a really big assumption, because, technologies improve over that time and methods improve. And so, for the sake of this analysis, it's fine to use the least common multiple, but, you should do it within reason as well. Okay. All right, so let's start. And so let's start our present worth analysis. Okay. And so we're going to take both of these cash flow diagrams and convert it into a present sum. Okay. And so let's start with A. Okay. All right. So if we're going to compute the present worth of A, we're going to take all the cash flows in this cash flow diagram on the bottom and then convert it into a present sum. Okay. All right. And so the first thing we have is our $7,000 initial cost, right? Okay. And so that $7,000 is already taking place in the present day. And so we don't need to perform any conversions on that. Okay. So that one's all good. Okay. Next, we have the $1,500 maintenance cost every year. Okay. Right. And so we're going to have a minus 1,500. Okay. And since this 1,500 here is a uniform series, right? And so it's something that's occurring every single year, we need to convert this A into a P. Okay. And so what we want is a P over A factor. Okay. Our interest rate in this case is 7%. Okay. And our N here, or the number of periods, is 12. Okay. Right. And as you can see here, I'm setting this up to be, so that we can actually look this up in the compound interest tables. Okay. Right. So this you would look up in compound interest tables. Okay. Right. And so that's the maintenance costs. And then now we have to put the salvage value. Okay. So the salvage value is going to be $1,200. Okay. And this $1,200 is a future sum, right? Because it's a single sum that happens in the future. And so we need to convert this to the present day. So we're going to do P over F, 7%. Okay. And then this future sum takes place in year 12, right? And so to convert this back to the present day, we need to set an N is equal to 12 as well. Okay. Where again, we're going to look up this value here in the compound interest tables. Okay. All right. And so let's go ahead and do that. And so let's you can't see it on my screen here, but I'm pulling up the compound interest tables. I'm going to the table with the interest rate of 7%, and I'm looking in the row for N is equal to 12. And what I see is that the P over A factor for this is 7.943. Okay. And then I go into that same row and I look up the P over F factor. I see that the P over F factor is 0.444. Okay. Right. And so after plugging in those numbers, this becomes just a simple arithmetic problem. And so you can just punch that into your calculator. And what you get is minus $18,381.70. Okay. Right. And so that's the present worth value for pump A. Okay. And so pump A, another way that you can think of it is that, accounting for all the maintenance costs and the salvage values at the end, choosing pump A would be the equivalent of paying out $18,381 today. Okay. And so that's basically the cost impact on today's value for option A. Okay. Okay. So any questions on this? Okay. All right. So now let's do the present worth of option B. Okay. So this one's going to be a little bit more complicated just because we have a little bit more going on. Okay. Right, so we have actually quite a few more future sums here that we have to deal with. Okay. All right, and so let's start with the initial cost, just like we always do. Okay, so for the initial cost for option B, we have an initial cost of $5,000. Okay. Right. Then we have our maintenance costs, and so actually let me peek back at the cash flow diagram here. Okay. We have a maintenance cost of $1,000. But this is taking place over the entire 12-year period, right? Because we're not having any gap in terms of purchasing the pump, and so we can just combine all of these 1,000 uniform series into just one, and so we can just say that this $1,000 right here, it's going to take place over all 12 years. Okay. And so we can do a P over A factor of 7% and 12, okay, because it's going to be over all 4 years. Okay. All right, question. So question in the chat. So what does it mean for PWA to have a negative value versus a positive sum result? Yeah, no, it's a good question. And so when your present sum is negative, that means it's going to be a net cost to you, right? And so what we're not considering in this problem is the fact that this pump is going to generate power for Southern California Edison, and they're going to sell that power. But we're looking at this as purely just from a cost perspective, and so we're not looking at any of the revenue that the pump is generating, and so we're just looking at saying which pump is going to minimize our cost. Yeah, and so a negative PWA just means that it's that's going to be the net cost basically in terms of today's money value. Mm-hmm. Right. Okay. And so that's the maintenance costs. Okay. Next, we have to account for the salvage values. Okay. Because basically with option B, we can say that we're going to sell the pumps for $1,000 at the end every 6 years. Okay. Oh, question in the chat. Okay, so for years 6 and 12, we are assuming that we are fixing the pump before salvaging it at the end of the year. So at year 6 and 12, we're assuming that we're buying a new one, and so we're basically going to be when you say salvage value, you're basically saying that you're getting rid of the pump and you're selling it to someone else, and then we're just going to buy a brand new pump that's exactly the same as the first one. Yeah. Mm-hmm. Yeah, and so usually for for these problems, when I say salvage value, we're usually not selling the pump for someone else to use, although sometimes that could be the case, and so you could sell it to like some poor students or something like that who can't afford a new pump, and so that's definitely a real situation. I've been on the receiving end of that, of just buying old computers that people don't want anymore for dirt cheap. Okay, and so it may be too old to use up to Southern California Edison standards, because they're a power producing company, and so they have pretty strict standards and government regulations for their pumps. But for dude in his garage that wants to use a pump for something, they're under a lot less standards, and so they could sell the pump to someone like that. Or another common situation is they can just take apart the pump and then just sell the parts for something. And so a lot of times those parts will still be okay or still be in working condition, and they can sell that to whatever vendors or people that are willing to buy it. Yeah. Yes. Yeah. So it's pretty often, and so a company different companies have different standards for their machinery, and so a lot of times they'll sell a machine that may not fit their standards anymore, but might be perfectly fine for someone else. Yeah, and so that's what I usually, and so that's usually what's happening when you have these salvage values. Yeah. Okay, and so we have our salvage value. So we have a salvage value of 1,000. Okay, and so the salvage value is a one-time payment. Okay, that's happening with a 7% interest rate. Okay, and so we want a P over F factor. And the first time we're going to sell the pump is going to be at 6 years. Okay. Okay. And so if you look at the cash flow diagram right here, if you look at this salvage value right here, okay, we can see that this is happening in year 6, and it's also just a one-time sale, right? And so what we want is a P over F factor for that. Okay. But we're also going to sell the pump at the end of 12 years too, right? And so this right here is the sale of the first pump. And then this right here is going to be the sale of the second pump in year 12. Okay, so this is going to be P over F, 7% and 12 years. Okay. Right. So I should say salvage. First pump. Okay, and this right here is salvage. Second pump. Okay. Right, and so we have 2 here, right? Because remember, we're buying 2 pumps, and so we need to sell both of them eventually. So we need to make sure that we account for both of them. Okay. Right, and you'll notice here that that this end value right here, this is the end of the first cycle. Okay, and so you need to make sure that you get the ends right, because it's it can be really easy to kind of miss them. Okay. All right. And so we're not quite done yet, okay? Because we have one more cost that we need to account for, okay? And that's when we purchase the second pump, right? And so when we purchase the second pump, that happened in year 6, right? As we go back to the cash flow diagram, we can see here that we have an additional $5,000 cost in year 6, because that's when we're buying the new pump, okay? And so we need to account for that in our present worth calculations. Okay? And so this is going to be another minus 5,000 P over F. 7% and 6 years. Okay. Right. So does that make sense about why we included all these different cash flows into this calculation? Okay. Okay. And so before, at this point, you can look up these converging factors in the compound interest table, but we can actually simplify this a little bit, okay? Because if you look here, if we look at these two values here, right? Both of these are P over F factors that happen in year 6, right? And so this factor here is actually going to be exactly the same for both of them, okay? And so you can actually simplify this a little bit. And so you can just basically say that instead of a positive 1,000 and a minus 5,000, for P over F in year 6, we can just say that we're just going to have a net minus 4,000 at that year. Okay, and so we can say that PWB is equal to minus 5,000 minus 1,000 P over A, 7%, 12. Okay, minus 4,000 P over F, 7% and 6. Plus 1,000 P over F, 7%, 12. Okay, and so all I did was I just combined kind of the 2 like factors together. Okay. Okay, and so you can do that to simplify your calculations just a little bit. Okay, and you can actually represent that in the cash flow diagram too, right? Because here you can see that we have a positive 1,000 and a minus 5,000 here. Okay. Because these cash flows are happening at the exact same time, and so they're both future sums that occur at the same time, then you can combine them, right? And so instead of having a positive 1,000 up here and a negative 5,000 down here, okay, what you can do instead is that because these are happening at the same time, you can just have a minus 4,000 down here. Okay. Right. And so that simplifies your diagram a little bit too. Okay, so because every year I kind of get questions about that. If when you're kind of layering so many arrows on top of the same time period, can you combine them into one? And the answer is yes, right? Because remember, any cash flow that occurs at the same time, any cash flow of the same type that occurs at the same time, you can combine them. Okay. And so the key here is at the same time, okay? And so we can't combine, the future sum with, we can't combine these two in orange with, the one in purple right here, okay? Because this one in purple here occurs at year 12, okay? And so that wouldn't be a fair comparison or a fair combination to make because they occur at different times. Okay? Yes, yeah. Yeah, so even though both of these, both the purple and the orange are both P over F, the fact that they occur at different times means that you cannot combine them, okay? Because if you look up the conversion factors in the compound interest table for 12 and for 6, they're going to be different from each other, okay? Okay, and so let's go ahead and look these factors up in the table, okay? And then let's plug these in, right? And so just like before, this P over A factor for 7% and 12, this is going to be 7.943 from the tables, okay? This P over F factor for n is equal to 6 years is going to be 0.6663, okay? And then this P over F factor for n is equal to 12 is going to be 0.444, okay? And so if you plug everything in and you compute the end result, you punch everything to your calculator, what you get is present worth of B is minus $15,164.20. Okay. And so now that's the present worth of B. And so now what we can do is we can compare this to the present worth of A. So let's go back. Okay. And we can see that the present worth of A is a minus 18,381. Okay. And so we can see here that since the present worth of B is less negative, that means the overall cost of going with vendor B is going to be basically $3,000 less. Okay. Right, and so by going with option B, even though we have to buy a new pump by year 6, we're actually saving the company, basically a little bit over $3,000 in present day money. Okay, and so for this problem, it's better to go with option B. Okay. And so I really like this example because when I was first writing this example and I was getting the numbers from the textbook, I was like, option B for sure is going to be less effective or less efficient just because you have to buy a new one and it's going to be a hassle to buy a new one and you have to set it up and that's another $5,000 in the future. But the fact that a lot of the savings comes from the fact that option B costs $2,000 less in the present day, right? Because if you look at the initial cost for option A, that was $7,000, and the initial cost for B is $5,000, right? And so that $2,000 that you save today is actually really, really valuable, right? And so even though you have to spend another $5,000 in the future, the fact that you save $2,000 today means that you can actually use that $2,000 to do something else, right? And so you can invest that money, you can do other stuff, right? And money that you have today is always going to be more valuable than money that you may or may not have in the future. Okay. Okay. Any questions on this?
Yeah, I have one real quick.
Yep.
I don't know. I think I zoned out or something, but could you explain one more time how you got the minus 4,000?
Yeah. So this minus 4,000 comes from the fact that if you look at these two quantities that I've boxed in orange right here, you have a plus 1,000 and a minus 5,000. But their conversion factors are exactly the same. And so they're both P over F 7% and 6. And the other one is P over F 7% and 6. And so when they have the same conversion factor, you can just combine them into one. Yeah.
Oh, okay, for sure. Thank you.
Yeah.
Professor?
Yeah, what's up?
I know that you want a justification for these kinds of problems. So did you just want us to justify by saying option B is better and that's it?
Yep. Yeah, and so when I say justification, what I meant is that I want you guys to pick something in the end, because I think the tempting thing when you're doing these problems, and you'll see in the homework too, I'm going to make you do more calculations than this. The tempting thing is to compute the present worth for everything and then just stop, right? You just say that I've done all the calculations, that's it, right? And so there's there's one more really small step I want you to do after that, is to actually pick the one that's the highest. And so I actually want you to explicitly write down that, this option is the best because it has the highest present worth. And so don't just stop by, don't stop after saying PWA is this and then PWB is this. Tell me that PWB is higher, so I want to choose B, right? I know it seems really pedantic and really annoying to do, but that's kind of what you have to do in industry too, because a lot of times you're going to be doing the calculations and then maybe forwarding this to your purchasing agent or your manager, right? And they don't really care as much about the numbers. They might look at them later, but what they want to get in your email is buy this one, right? And so they don't just want to see a bunch of calculations. They want to see, buy this one because it's the best one. And so that's kind of what I want you guys to do.
Right. Thank you.
Mhm. Option B. Then you can use that a little bit, but I don't want random people from industry calling me and asking me why you guys pick something. Yeah. Okay. All right. And so remember, although before we kind of move on, I want you to kind of remember one really big caveat with this example is that one really big assumption that we made here for option B is that this pump is going to cost exactly the same in year 6 as it does today, right? And so that's of course the really, really big assumption. And so just kind of take these results with a grain of salt. But for this case, because the difference is so big, like $3,000 is a pretty big difference. Any increase in cost for the pump should still be okay. So option B should still be the best one, unless of course it like doubles in price or something. Okay. All right, and so that's basically what you have to do when you are faced with example with different product lives. Okay. And so that's basically the least common multiple technique. Okay. But the least common multiple technique is not going to work out all the time. So actually, Danny gave a good example earlier today of, what if the least common multiple is 30 years? Is that still reasonable? And so, for 30 years, that's something where you might have to start thinking about maybe you should approach the analysis a different way. But I'll give you an even more extreme case, right? And so let's say that you're comparing two options. Okay. And so let's say option A will last 7 years. Okay. Meanwhile, option B will last you 13 years. Okay. Right. And so the least common multiple between these guys is 91 years, right? And so these are both awesome prime numbers. And so, the only common multiple between them is if you just straight up multiply them together, which is 91 years. Right? 91 years is the lifetime of a good, healthy person. And so to say that you're going to do an economic analysis over that period of time is really, that's a big risk, right? Because if you think about where we were kind of as a society 91 years ago, I don't think we're using anything that was built back then, except maybe like, public infrastructure, like maybe the roads or, the pipes or something like that. So, something like a pump or like an automobile, I don't think we're going to be using those 91 years in the future. Okay. And so, when your least common multiple is something extreme like this, then there's a different way that you can approach the problem, and still do present work. Okay. And so in this case, 91 years is too long. Is a little bit too long to do with the least common multiple technique. Okay. All right. And so what's more realistic in these situations is instead of using the least common multiple, instead you should just straight up use the amount of time that you expect to use the equipment. Okay. Right, and so it makes a lot more sense to say that, we only plan on using this machine for 10 years, and so let's perform our analysis for 10 years for both. Okay. Right. The downside to this is that you're not going to be using the machines all the way up until its end of life. Okay, and so you're inevitably going to have to sell the machines before it's used up. Okay? Or in other words, we're going to have to salvage the machines earlier than its intended life. Okay. And because of this, you're going to have to estimate kind of what's called an early salvage value. Okay. And so basically, you have to estimate that if we're only going to use this pump for maybe 5 years, right? Whereas normally this pump was going to last us 6, 7, 8 years. How much is it going to be worth at 5 years versus if you use it all the way up? Okay, and this is usually kind of difficult, and so it's there's no kind of systematic way of doing this, because it really depends on what the part is and the nature of how you're using it, and so estimating an early salvage value kind of requires a lot of domain specific knowledge that I can't that is kind of outside the scope of this class. And so for our sake, for just from the perspective of pure economics, usually I'll be giving these to you. Okay. Okay. Right, but just kind of know that if you do come across this issue in industry, that that estimating how much it's going to be worth before its time is up, that's something that you're going to have to do. Okay. All right. Any questions on this before we do an example? Okay. All right. So let's do an example just to kind of show this thing. Okay. All right, and so let's say that we work for a diesel manufacturer, and then we're choosing between 2 different production machines. Okay. All right, and so this case we'll call it option 1 and option 2. Okay. And just to keep things simple, we're only going to consider just the initial cost and the salvage value. Okay. Okay. And so let's say option 1 has an initial cost of $50,000. Okay. Whereas option 2 has an initial cost of $75,000. Okay. Next, we have the salvage value, and these are going to be the end of life salvage values. And so if you use up the machine all the way up until its end of life, this is how much you can sell for. Okay. And so let's say option 1 has an end of life salvage value of $10,000. Okay. And then option 2 is $12,000. Okay. Right. And then let's say that option 1 will last you 7 years. Okay. And so that's going to be its useful life. And then option 2 will have a useful life of 13. Okay. And so this is the exact situation that we had on the previous page, where the least common multiple between these guys is 91 years. And using the same machine for 91 years, buying a new one that many times is just not It's just not realistic. Okay. All right. And so because the the least common multiple approach is not realistic, the company says that, okay, realistically, we expect to be using these machines for 10 years. Okay. Okay. And so 10 years is going to be the basis for our analysis. Okay. And so for both option 1 and option 2, we're going to consider, an analysis for 10 years. Okay. All right. And so because, we're kind of ending this kind of in the middle of the product's lives, okay, then, you have to estimate what their early salvage values are going to be. All right. And so for option 1, let's say that if we salvage it after 3 years of use, okay, okay, after 3 years of use, if we salvage it, then we are going to get a salvage value of $20,000. Okay. And then for option 2, since option 2 will last us 13 years, then, if it's going to last us for the entire 10-year period. And so if we salvage this guy at year 10, we'll say that it's going to give us $15,000 back. Okay. Okay. All right. And so if we assume an interest rate of 8%, okay, let's use present worth analysis to determine, which one is going to be the more economically efficient option. Okay. And so here, we have a situation where the product lives are different. And then, we're going to use these early salvage values in order to do our present worth. Okay. All right. Any questions on this? Okay. All right. And so let's start by drawing the cash flow diagrams for both cases. Okay. And then from there, we can compute its present sum. All right, and so let's start with alternative 1, or option 1. Right, so let me draw the cash flow diagram. Okay, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so for option 1, we have our initial cost of $50,000. Okay. And so that's going to be something that we're going to purchase today. Okay. And option 1 is only going to last us 7 years, right? And so at the end of year 7, we're going to need to buy a new pump in order to get us to the end of 10 years. Okay. And so in year 7, we're going to do another purchase of $50,000. Okay. And then we're also going to have our salvage values, right? And so we have 2 different salvage values here. So we have one that occurs at year 7, okay? And then we're gonna have another at year 10, because we're gonna be selling the second pump, right? All right, so let's look at the first pump first. And so we're gonna use the first pump all the way up until its end of life, right? And so we're gonna use our pump for the full 7 years. And so the salvage value that we put here is actually the end of life salvage value, which is 10,000, okay? Whereas the second pump, we're only going to use for 3 years, right? And so we're going to do 8, 9, 10. Okay. And so the salvage value at the end of that time is going to be 20,000. Okay. And then similar to what we did before previously, if we can simplify this a little bit. And so instead of having 2 arrows here on year 7, what we can do is we can combine them, right? We can combine them because they take place at the exact same time and they're the exact same cash flow type. And so instead of having 1 up arrow at 10,000 and 1 down arrow at 50,000, you can just add them together. Okay. And then we're just going to have 1 cash flow there that's going to be 40,000. Okay. All right. And so let's compute the present worth for option 1. Okay. Right. And so we're going to convert all of these into a present sum. Okay. All right. And so first we have our minus 50,000. And so that's occurring at the at year 0. And so that's already a present sum. And so we don't need to convert that guy. Okay. Next, we have our future sum of minus 40,000. And so it's going to be P over F. What was the interest rate? 8%. Okay. And that's going to occur at the 7th year. Okay. Then we have our salvage value at the end of 10 years. And so that's going to be 20,000. Okay. P over F, because we're converting from a future sum to a present sum, 8% and 10 years. Okay. All right. And so we can look up these factors in the compound interest tables. And so this P over F, 8% and 7, this is going to be 0.5835. Okay. And then our other one at 10 years is going to be 0.4632. Okay. Right, and so we do those calculations, and what we get is minus $64,000 and $64,076. Okay. All right, and so that's alternative 1. Okay. Now we have the one for alternative 2. So let's go ahead and draw the cash flow diagram for that one. Okay. Yeah, the first one is 0.5835. Yeah. Mm-hmm. Okay, and so for option 2, we have a very simple cash flow diagram here. Okay, because for option 2, option 2 here has a useful life of 13 years. Okay, and so that's going to last longer than our 10-year period. And so the only 2 cash flows that we have here are going to be the initial cost. Right, and so the initial cost is going to be $75,000 here. Okay, and then we have the salvage value at the end. But since we're salvaging early, right? We never reach the end of life here. This is just going to be purely the early salvage value. Okay, and so this is $15,000. Okay, and so very, very simple. Okay, so we just have 2 cash flows, one of which is already in present sum. And so we just have to perform 1 single conversion. Okay. All right. Any questions on this example so far? Okay. All right. And so let's go ahead and perform that conversion. Okay. And so let's compute the present worth of 2. Okay. So present worth of 2 is going to be A minus 75,000. Okay. Already in the present sum, so we don't need to convert that. Okay. Next, we have a positive 15,000. Okay, and this is going to be P over F, 8% and 10 years. Okay. Right. And so this value, we've already looked it up in the table from the previous part, and so this is going to be 0.4632. Okay. And so we plug everything in, and what we get is minus $68,000 my $68,052. Okay. All right. And so if we compare this number to the present worth of option one, go back a page real quick, we can see that the present worth of option one is a minus 64,000. Okay. And so option one here is going to be greater or going to be better by a margin of $4,000. Okay. So option one is better. Okay. Right. And so for cases where the least common multiple approach isn't appropriate, then you're probably going to have to use an early salvage value approach here. Okay. And once again, you see that even though option one is something that it's not going to last us for the entire time, the fact that it's $25,000 cheaper in the present day, is a really big money saver. Okay. Okay. Any questions on this? All right. And so that's that's how you handle situations where the time period's different. Okay. Now let's go over kind of a very special case. Okay. And that's the case of let's say that instead, now that we have a time period that's infinite. Okay. Okay. All right, question. So these problems are still under the assumption of no inflation or taxes. That's correct. Yeah. And so we're still assuming that there's no inflation and no taxes. Yeah. So we'll work those in later on this semester. And so these types of analysis where you're kind of doing a present sum analysis of something with an infinite time period, they're called capitalized costs. Okay. Okay. All right. And so, these are situations where, you're going to have an engineering project where the expected life is so long that it's actually just more useful to consider it as infinite. Okay. Okay. Right. And so, that might seem kind of crazy, but this is actually pretty common for public works projects, right? And so if you think of like the roads, or you think of like the pipes and the sewage systems, right? Those are not systems that, the government can just say, I'm going to sell the road to somebody and then just buy a new road, right? And so those roads are just going to be there forever. But, of course, they're going to maintain the roads and they're going to, service them throughout all the years, but it's not really the same as like a pump or like an engine or like an automobile that you can sell and just buy a new one, right? And so these are kind of big kind of permanent fixtures that that you expect to kind of be maintaining them for forever. Okay. And so for those situations, you can kind of assume that the product life is just infinity. Okay. All right. And so what's common in these situations is that because they're going to be maintained and and serviced for for all intents and purposes for all of eternity. Okay. A lot of times it can be convenient to to set aside money now, or to set aside money at some time, and then there's going to be a very large sum of money, and then what you're going to do is that you're going to collect interest on that very large sum of money, and then have the interest cover all the maintenance costs. Okay. All right. And so the term for this is capitalized cost. And so capitalized cost is basically the amount of money you would set aside now at some interest rate in order to yield a uniform cash flow indefinitely. Okay. And so basically what you're doing for capitalized costs is that you're taking a very large sum of money, you're depositing it into a bank account, okay, or some kind of investment. And then all you're going to do then is you're going to collect on the interest payments, every year or every month or so. Okay. Right. And so in order for this to work, you would basically only withdraw the interest payments made from that year. Okay. All right. And so on the next page, I'll do kind of a very quick example just to show you, what I mean by this. Okay. All right, question in the chat, endowment. Yes, actually, that's I was going to bring that up. And so, probably if you've, you guys have all been here for a while now, and so you probably heard Cal State Fullerton brag about its endowment at some point, right? And actually, I actually pulled up the report from this year, and actually, the endowment right now for Cal State Fullerton sits at about let's see, $73 million in book value. Okay, that means what that basically means is that the school has a fund that has $73 million in it. Okay, but they're not going to use that $73 million for anything. Okay, and so what they're doing is that they put this large sum of money into an account, and then each year they're making interest payments on that account, right? Because they've invested that money into stocks, into bonds and stuff like that, and then each year they have interest payments coming in. Okay, and then what they do is that they take those interest payments, they withdraw those from those accounts, and then they use that to support some campus functions. Okay, and so whenever you hear universities say that we have so much money in their endowments, that's actually money that they're not touching. So they actually don't plan on withdrawing that money anytime soon. But what they're doing instead is that they're withdrawing the interest rates. Okay, and so it's really kind of just a form of passive income. You have kind of a large sum of money, and then that's going to be generating some passive income, for you to use for other stuff. Yeah. Mm-hmm. Yeah, I'll do kind of a smaller example on the next page. Okay. All right, and so let's do an example kind of with that's kind of a little bit easier to grasp. Okay, and so let's say that you have, maybe you found it on the street, or maybe you won a radio contest or something, but you suddenly come into possession of $1,000. And then with that $1,000, you're going to deposit it into a bank account. Okay. And this bank account has an 8% interest rate. Okay. I'll say annual. Okay. And so what that means is that each year, just by the fact that your $1,000 is sitting in this bank, and then the bank is going to be paying you 8% of your $1,000 every year. Okay. Okay. You can then withdraw that $80 each year and then use that for whatever, right? Maybe go out to a nice dinner, maybe throw a nice 21st birthday party, right? Buy the booze for the party, right? And so that's $80 that you're basically having each year just by the fact that you deposited a large sum of money into the bank. Okay. And so in this example here, the $1,000. Okay. This $1,000, this is your large amount of money that you're setting aside now. And so this is your capitalized cost. Okay. And then the $80 per year, this is your uniform series interest payments. Okay. All right. And so basically, the formula for this is that, you basically have two components here to the capitalized cost. And so you have one part P, where P right here, this is your principal amount, or this is the large sum that you're putting away. Okay. Okay. And the important thing for capitalized costs is that you do not touch this. Okay. And so you don't touch the original amount. Okay. And then on top of that, each year you're going to be making the interest payments. And so that you're basically just going to take the interest rate and you're going to multiply it by your principal amount. Okay. And so this right here is a uniform series. A. Okay. And so if we just take this portion right here, okay, we can say that the uniform series amount is equal to IP. Okay. We can use this to compute the capitalized cost, right? And so let's say that you want a uniform series payment from an endowment or something to be equal to, let's say $500. Okay. And so you want to compute how much money that you need to set aside now in order to passively generate that $500 each year. Okay. And so the way that you can do that is you can just take your uniform series amount that you want and then just divide by I. Okay. Okay. All right. Any questions on this before we do another example? It's funny, if you guys were following the news over summer, you probably heard that Mackenzie Scott donated Cal State Fullerton $40 million from her fund. My fiance's dad always asks me, what is? I heard that Amazon's wife donated your school $40 million, and I said, yeah, that's true. Amazon's wife, former wife, I guess. And so he asked me, are you going to be getting any of that money? And I said, no. Probably most of it's going to go to the endowment, so that it's going to generate more and more money. But it's always flashy, and it's always kind of a big news story when university receives a big donation. But usually the students or the staff there or the faculty, they usually don't see any. It just goes into the endowment, and then that gets used for other stuff. Yeah. For him, it's easy because he's a businessman, and so he thinks of things in terms of big companies, and so when he thinks of I don't think he even knows Jeff Bezos' name. I think he just calls like Amazon boss. I think that's what he thinks of it. Yeah. Yeah, parking structure. Yeah, they're doing a lot of construction around campus. So yeah, we'll see. Okay, so let's do. I think we have time for one more example. One more example before we end today. And so this is kind of a more realistic case of how a city would use capitalized cost to maintain its infrastructure. Okay. All right, and so let's say that you work for the city of LA. Okay. Right. And so let's say the city of LA is planning to build a new pipeline to transport water from, let's just say Nevada. Okay. Okay. All right. And so the pipeline will have an initial cost of $8 million. Okay. And so, right away, we know that, our initial cost is 8 million. Okay. And then, this pipeline is going to have to be completely overhauled, completely replaced every 70 years. Okay. And so we have a really, really long horizon. Okay. It's going to be replaced every 70 years, and and let's assume that we're going to use this pipeline for all of eternity. Okay, so every 70 years you're going to have to pay $8 million. Okay. All right, and so if we assume our interest rate is 7%, yeah, 7%. Okay. Let's compute the capitalized cost that's needed for both building and maintaining this pipeline. Okay. All right. And so let's start by drawing the cash flow diagram. Okay. And so because this nothing's really going to happen for this pipeline for 70 years, and so I'm going to use these dots. Okay. Okay. And so, we're only really going to have any action, every 70 years. And so, I'm just going to skip ahead for those ones. Okay. We know that today, we have to actually build the pipeline first, right? And so this is going to be $8 million. Well, 8 million. Okay. Then at year 70 and year 140 and year 210, okay, it's going to cost us $8 million again. Right? And so it's going to be 8 million. This is going to be 8 million. Okay. This is going to be 8 million. Okay. And that's going to continue on for all of eternity. Okay. All right. And so, what the city wants to do is that, they just want to set aside an amount of money right now, today, in order to kind of pay for this pipeline for forever. Okay. And so they just want to collect on the interest payments and then use the interest payments to pay for the pipe. Okay. And so, we already know for sure that we need to pay at least $8 million already, because that's gonna be what it's gonna cost to build it at first, right? But all the other ones, okay, you can kind of think of this as kind of like maintenance costs, okay? But these maintenance costs are only happening every 70 years, okay? And so if we consider these future payments as future sums, let's convert these into a uniform series payment. that's a little bit easier to kind of parse. And so if you think of these kind of future costs as, you know, maintenance costs that you're gonna have to pay every year, you know, that's a little bit easier to parse, and it's gonna be easier for us to compute our capitalized costs as well. Okay. So let's convert this to uniform series. All right. And so basically we're going to be computing A, okay? And so this A is going to be 8 million, okay, times. And so we want to compute an A, and we're converting from an F, right? And so we need an A over F factor for I is equal to 7%. And we're just going to consider the one at 70 years first, because, you know, we're going to assume that that's for each 70-year period is kind of its own thing, right? And so we only need to compute, you know, for the first 70 years, and then that's going to be kind of the same, you know, everything after that, right? All right, and so if we compute this number, we get simply an amount of $4,960 per year. Okay. And so completely replacing this pipe every 70 years is what we're saying is that's exactly the same as paying almost $5,000 each year for those 7 years. Okay. And so this is a little bit easier for, you know, the city to budget, instead of saying, you know, every 70 years we have this huge cost, right? And so this is kind of the same thing as saying that we need $5,000 per year in order to pay for this. Okay. All right. Any questions on this so far? Okay. All right. So basically, you know, what we just computed is we said, in other words, we need $4,960 each year to cover replacement cost. Okay. Right. And so the city wants to set aside the money now, right? And so they basically just want to put, you know, a certain amount of money into an account right now, and then just withdraw the interest payments every single year in order to pay for the replacement every single year. Okay. And so let's compute the capitalized cost that's needed to make this happen. Okay. And so let's use the formula that we had on the previous page. And so our capitalized cost is equal to our A divided by our I. Okay. And so we're going to take our 4,960 and divide it by our interest rate, which is 0.07. Okay. And that gives us $71,000. Okay. All right. And so if the city sets aside $71,000 and collects the 7% interest every single year for 70 years, then it's going to have all the money that it needs to pay for this pipe's replacement. Okay. And so the total cost for this pipeline is going to be the initial $8 million that we used to buy it, plus this capitalized cost. Okay. 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 And so this right here is the initial cost. And this right here is the capitalized cost. Okay. The capitalized cost used to pay for the maintenance. Okay. And so if you add these together, what you get is $8,071,000. Right? Any questions on this? Okay. All right, and so you guys should be good to go for the homework now. And so the only thing that I didn't cover in the lecture notes here is cases where you have more than two alternatives, right? And so In the homework, you'll see I'll give you some problems where you're considering between 3 and 4. But those are pretty easy. The only thing you have to do is you just have to compute the present worth more than once. And then among those 3 or 4 different present worths, you just choose the highest one. And so, there's really nothing new to it. It's just you're doing more calculations for that. Okay. All right. And so that's all we got time for today. And so thank you guys for tuning in as usual. And so, get started on the homework. Let me know if you have any issues. Have a great weekend, especially for those of you who are partying this weekend. Have fun, stay safe. Okay. Come back on live next week. All right. That's the most important thing. And I'll see you guys next week.
Thank you, Professor.
Thanks,
Thanks,
Professor.
guys.
Thank you.
Thanks.
Have a nice weekend.
You too.
Professor, I have a quick question.
Sure. What's up?
Can you go back 2 pages?
Yeah.
Yeah, right there.
Mhm.
I know that the statement says $80 is what you get back on interest. Is that A?
Yes.
Oh,
Yeah.
okay.
So this $80, you can consider it as like $80 that you're making every single year. And so
Oh,
since
okay.
it's a uniform payment, then it's basically A, which is your uniform series.
Okay, thank you.
Mhm. Thanks, guys. Brandon, did you have any more questions? All right, I'll see you next week then.